Hi, everyone, and welcome to this Climos webinar. I'm going to introduce myself and also going to introduce the colleagues that are going to host the webinar together with me. I'm Oscar David Kirstein. I'm the head of the Medical Entomology and Parasitology Lab at the Ministry of Health in Israel. Together with my colleagues here, so we will guide you through one of the most, I guess, and I like to say that all the time, one of the most fascinating and challenging intersections of climate, ecology, and public health together. The objective of this webinar is simple but very ambitious. So it's not going to be short, it's going to be long, so you can stay here as much as you want. But it's going to be recorded, so you can go back anytime you want to see that. As I say, the objectives are to understand actually how sunfly reservoirs and human interact in a complex landscapes, to learn how surveillance, ecology, and management strategies can make differences between climate change, human expansion, wildlife, and neglected disease, and how to our health perspective is not a buzzword, but a daily necessity sometimes. By the end, I want you to see sunfly not just like tiny biting insect, but as powerful connectors actually between climate change, human expansion, wildlife, and neglected diseases like Leishmaniasis. And yes, we will also talk about rock piles, as the title is in the shadow of the rock pile, sunfly surveillance, reservoirs, and public health. Because sometimes the biggest public health battles start in a small crack, actually, of stones. So let's move forward. Just a little bit introduction about I introduce myself, and I'm going to introduce also Alon Ber. He's the senior pest management coordinator at the Pest Control Division in Israel Ministry of Environmental Protection. And Shirley, as I said, also as part of the Medical Entomology and Parasitology Lab here in Jerusalem Public Health Laboratories. So let's start with this big word, and I'm going to give a short introduction about this disease. I always go to some talks, and we give always the same introduction, but as much as I can't be surprised, it's still not clear, and many people don't know the disease. So Leishmaniasis is a group of disease actually caused by a protozoan parasite of the Leishmania genus. They are transmitted by the bite of infected female sunflies. They can affect the skin, the mucous membrane, or internal organs, depending on different species of the parasite. Over 1 billion people at risk in the endemic areas, and around 1.3 million new cases every year. We have two different formal cutaneous of leishmaniasis. We have cutaneous leishmaniasis with around 60,000 to million new cases annually. Visceral leishmaniasis with more than 50 to 90,000 cases with up to 40,000 deaths actually each year. Think about that, actually. More people die from visceral leishmaniasis than from some other diseases that actually dominate the news. But they're still classified as neglected tropical diseases, invisible actually, until a phase or a family or a community actually face them. These are actually steering figures, and they're only cover the human side, as you can see in these statistics. As a disclaimer, these numbers are pretty old, because as I said, neglected tropical diseases is very hard sometimes to go and cope up with reviews or some very updated information about how many cases of this disease circulate around the world. But here is actually a key missing from this slide that we can see here. We also have what we call canine leishmaniasis. And in countries across the Mediterranean, Latin America, and of course here also in the Middle East, dogs are not only victims, but are also the reservoirs of infection. Like, for example, in Southern Europe alone, hundreds of thousands of dogs are infected with Leishmania infantum. In Brazil, canine leishmaniasis is so widespread that it actually drives human focal epidemics or outbreaks. Here in Israel, canine cases outnumber humans once many time over sometime, but making them the real sentinel for public health. So while the slide shows the human burden, we need to remember that actually we cannot understand leishmaniasis without including dogs and also other animals, as we will see through the presentation. Human numbers actually are half of the story, is the tip of the iceberg. Just the normal generalized life cycle. But everything begins with the sandflies. When a female sandfly actually bite an infected host, in this case, I place there a human, but could be also any other animal, vertebrate, sorry. And the sandflies actually intake the parasite, and this parasite transformed from amastigote to promastigote. But the sandfly feed again that actually inject those promastigote in the new host. Once inside the skin, actually, they are taking up at macrophages. They are here the trick of the disease, actually, I like to call it, because instead of being destroyed, the parasite transform back actually into a mastigote and multiply there inside this little house that protect them. We have different form of leishmaniasis. We have cutaneous leishmaniasis, which actually produces skin lesions, sometimes self-healing, but leaving some scars. Mucocutaneous leishmaniasis, more destructive, involving the nose, mouth, and throat, is very common in areas in Latin America and the Amazonian, in Peruvian Amazonas. Visceral leishmaniasis or calazar, in human visceral leishmaniasis or calazar, actually, is the most severe form, spreading to the spleen, liver, and bone marrow. It's fatal for is when we leave it untreated. But now notice that actually the reservoir in the cycle, in most cases, leishmaniasis is zoonotic, so we call zoonotic leishmaniasis. Dogs are the major reservoir for Leishmania infantum, rodents, Leishmania major, hyrax, and Leishmania tropica in different places. But there are also concept of what we call anthroponotic cycle, and that's what we see in that corner here. Where humans themselves can act as main reservoirs of the disease. This is clear the case of Leishmania donovani, for example, which actually is the main causative of the etiological agent of visceral leishmaniasis in South Asia, in India, Nepal, Bangladesh, for example. The cutaneous leishmaniasis, especially caused by Leishmania tropica, is more controversial in some regions like in Afghanistan, Iran, Syria, Turkey, part of Morocco also. Outbreaks occur in dense urban settings without actually clear animal reservoirs. In those places, the evidence actually suggests that human may sustain the cycle directly. But in this area, in Israel, for example, and much of the Mediterranean, we know that some other reservoirs some other vertebrates are the one who actually sustain the cycle of the parasite. And that is why actually understanding the cycle is more than academic. It's tell us where we can and can't actually break the transmission. And that is actually where we can break the transmission, and where we try to break the transmission is all about what we're going to try to talk about today. As you can see, we have we have different main players in this cycle. We have humans or vertebrate, the flies and the parasites. We can see them as little pieces of a big puzzle. And we will try to see if we can actually put them together, how we can actually separate them, and what is the implications for putting these pieces together or trying to separate them. We're going to start between the vector and the parasite. And as we can see, just a short introduction, we have two different big group of these vectors, which are some flies. We have Tsutsumai in the New World and Phlebotomus in the Old World as the main genera. They don't only transmit Leishmania, but also transmit some flavivirus like Toscana virus, Naples virus, Sicilian virus, meaning one tiny fly can cause both parasitic diseases and viral meningitis. That is incredible. And that's why some flies are not just like little mosquito causes. They are like a whole different treat portfolio that we need to take into consideration. Some few points that I would love to touch about sunflies biology, and for you to understand then how hard and how difficult is to combat them, and it's not like a mosquito. So just in general point about sunflies, we know that they are like they have a complete life cycle. They have eggs, larvae with different stages of larvae, a pupa, and then an adult. They are about the third size of the mosquitoes. They are weak flyers. They rarely go further than 300 meters from where they hatch, but they don't fall by, but actually don't fall by their size. They within short flight ranges, they can actually link together rodent burrows, hyrax colony, dog kennels, and human houses. That it's all it takes for the transmission of this parasite. They breed actually in dark, moist soils with organic matters. That's what we think. These burrows crack in walls, compost pile, but actually here is the truth. After a decade of research, the natural breeding sites are still not fully elucidated. The mysteries make control actually a real challenge. So we know that they breed on the soils on specific cracks with high organic matter, but we don't know yet. All we know about their biology and the developmental biology is by insectariums. Now, about feeding males, just feed on plant like honeydews or sucrate plant juices, while the females actually need the blood to develop their eggs. So that actually why the blood feed. And the female actually is the one who transmits the pathogen. They are opportunistic feeders. That means they will bite whatever is easy to reach, people, dogs, rodent, foxes, whatever. But some of them, surprisingly, specific species, they have specific preferences for some host. That's why actually more than 70 animal species will be actually identified as reservoirs of the parasite, of Leishmania parasite. Actually, most sunflies feed outdoors at dusk, night, but some species will bite indoors also, even during the day. And out of about 500 known sunfly species, only 30 are proven vector of Leishmaniasis, but those 30 are enough actually to cause millions of cases worldwide. Finally, actually, zoom out to the big picture. Sunflies thrive in warm and temperate regions, and climate change and urbanization or expansion of rural environments are pushing them into new places. Every new construction site, every pool managed rock pile that we live aside, every shift in temperature, rainfall actually can make a tremendous change in their biology and their spread. It can all mean like new sunfly habitat closer to people. So for public health, the risk is hyperlocal. An outbreak isn't about the whole city suddenly swarming with flies. It's about the ecology within few hundred meters from where they are located. A rock pile behind the house, a burrow under a wall, a kennel of dog edge, for example, in the village. That's why local surveillance and interventions are everything to sometimes control these little spheres. Moving forward, I'm going to focus my talk on this region in Israel, especially because it's like a perfect laboratory. Despite the very small size country, it has an incredible diversity of sunflies across multiple subgenera, as you can see here for this list. Here we see that actually from Phlebotomus papetasis, urgenti, Phlebotomus syriacus, Topi, Perfil and more. Each species actually is connected to different parasites and reservoirs and specific habitat preferences. That is incredible. There are key puzzles, not one sunfly, no one parasite, no one reservoir, but actually multiple overlapping cycles happening all the time in different regions. And for public health, this means we cannot actually cope up with a single control method. We cannot do a copy paste of a control method and apply it in different areas. We have to match species, ecology, and diseases from different for every region. Actually, that's a small, especially in this very small area. Well, it's not especially; it's actually more interesting in this small area. But going further, the question is, with all this diversity, which flies actually matter for transmission in Israel, but also in other areas actually may share the same sort of environment, like a Mediterranean environment. So the answer that actually lets to answer that, I think we need to walk through the main transmission cycles of these diseases. I will focus in Israel, but this could be applied to different other areas somehow. We will start with the first transmission cycle we have in Israel. As you can see, the first transmission cycle is the main actor here. Sorry. The first vector we're going to talk about is Phlebotomus papatasi. This is the classical desert sunfly adapted to arid zone, very close related to agricultural areas. The map on the side is actually, you will see a predicted distribution of Phlebotomus papatasi based actually on ecological niche modeling. The warmer color or red and orange indicate higher sustainability, which actually each a black dot that will appear after confirm occurrence of records of positive sunflies. We are actually looking at the model that combines present data with climate and landscape cover and predictive risk zones across the whole region that actually predict the whole map. So the main parasite that actually is transmitted by Phlebotomus is linked to Phlebotomus papatatis leishmania major. Is the agent of actually what we call zoonotic cutaneous leishmaniasis in Israel. These produce, as I said, cutaneous leishmaniasis, skin lesions that may actually heal, usually leave a very big scare when it's actually in the area of the face, also in the hands. The reservoirs are desert rodent, like fat sand rat, Wagner gerbild, gert, and other like balls. The burrowing rodent are essentially for the cycle. Without them, Leishmania major cannot persist. And the biotope, as you can see in this short video, is like low relief desert soils, friable and cohesive enough for rodent burrows. This is where flies breed somehow, rodents digs, and actually the transmission thrive. The second cycles we're going to see is related to Phlebotomus argenti as a main player. Just a minute. And Phlebotomus argenti is actually the vector of Leishmania tropica. The map on the side shows us the same thing as I explained before. They cause cutaneous leishmaniasis as well, but with very different ecological niches or scenarios than Leishmania major. The reservoir here is there are rock hyraxes. Those little cute people may call them rats, but they are not rats. I call them elephants because cladistically they are cousins of elephants, some structures on their legs. But they're very interesting animals. Unlike the rodents, these hyraxes thrive in rock piles, quarries, retaining walls, many of them created by human during constructions. As you can see, the biotope. And another interesting point about this that we also think that Phlebotomus arabicus may also be a vector of Leishmania tropica, is specifically in the northern area of the Galilee Sea of Galilee. Sorry. As you can see, the biotope here is highly on rocky slopes, often at the edge of town and villages. And the background video actually shows exactly what the rocky escarpment and where hyrax colony live side by side to human villages or cities sometimes. Um, Going further to the third cycle we have in the area, where we have here a suspected vector, not elucidated to the end, but like highly confident that those might be the vector for Leishmania infantum, Plebotomus tobi. This actually caused the Leishmania, the visceral Leishmaniasis or canine actually Leishmaniasis in the area. It's deadly from a disease affecting the spleen, liver, bone marrow of dogs. The reservoirs are canine and domestic dogs, as well as like jackals and foxes. Dogs are actually particularly important since they breach the parasite in households areas and can actually transmit to produce or the occurrence of human cases, which actually in nowadays is very low prevalence. Also, we need to talk about another two potential vectors, as Phlebotomus syriacus and Phlebotomus perfilevi galileus is missing an S at the end. Sorry for that. A biotope of this is more in the central area of the country, as you can see, is a very, very well Mediterranean environment. Villages, forests, and peri-urban zones, areas where humans and dog and wild canids actually can interact very close to each other. What you see in the background is actually part of the sea organic. And we have a fourth cycle that actually was discovered not a long time ago. It's a very well, it's less well-known cycle. The main suspected vector here, and it's a very suspected vector, is Phlebotomus alexandri. And yes, we have a new invitee here in the area, it's Leishmania donovani. This can cause both cutaneous and visceral form. For now, we have an indication that actually produce a cutaneous form and hasn't produced visceralization yet. But we located Leishmania donovani in Israel, and the main point of Leishmania donovani that actually is the main etiological agent of Kala Azar or visceral leishmaniasis in Sudan, Ethiopia, and India. The very interesting point is that it's very restricted to the southern part of the country in the Negev desert, very lower to the what we call the Ramond crater, which is not actually a crater, but is a formation. And the main reservoir, a suspected reservoir here, is the European hare or Lepus europaeus. This is very unusual. Most Leishmania nodomani cycles are like anthropomorphic, what we know around the world, human to human. But in Israel, it seems that the evidence suggests that hares may be or maintain the parasite in nature in those very remote desertic areas. And what is more interesting that it's only been found in this desertic area here. So the biotope is a low relief soil, friable, is yet cohesive, where hares dig and sandflies actually breed on those burrows. The background like landscape, as you can see, are exactly the type of biotope Therion with this cycle plays around. Let's enjoy it a little bit. Forward. Here is actually the big picture of the epidemiology of the leishmaniasis in the country. Until 2000, continuous leishmaniasis was very limited. Between 2001 and 2005, it started expanded. In 2006, between 2006 and 10, even more in 2010 to 2024, actually, it became an entrant in new areas. This expansion is linked to urbanization and growing of agricultural area, road construction, lands use change. Every quarry actually, housing projects and hill shield actually catches the more places for hyrax in the north, rodents in the south. As for, oh, sorry. As for visceral leishmaniasis, it's remain in specific areas, but canine VL is actually widespreading. That's why our surveillance must cover actually dogs as well as people. The risk is already present here. Leishmania infantry in Canada is very well known in specific areas in the central south part of the country. And now, having Leishmania donovani here, we have at risk of another very prominent Leishmania cycle. Challenges. I think we share the challenges here and across the whole Mediterranean area, or Europe, or any other country that actually faces leishmaniasis as a public health problem. First is an stigma, actually. CL is not usually fatal, but scares are for life and sometimes very, very, very deep. But they can actually create or are prompt to secondary infections. We saw people that we did so many bites on their hands that actually almost they loses their hands. Terrible pictures, terrible picture of the development of this disease. So secondary, the diagnosis and the treatment are quite limited and often not optimal. We used to have here a cream called Leishkutan, but it's being stopped, not produced anymore because it's been proven, or it's been seen that some of the Leishmania forms have created some sort of resistance to the cream, so they start producing because it's not working anymore. So early diagnosis is not rare, but it's like sort of limited until the scares appears. Access to safe drugs is uneven in many other countries also. The vector control is difficult. Some fly population actually increasing, the range are expanding, and multiple species are involved. For the reservoir ecology is very complex. Hyraxes, dogs, foxes. You cannot just take care of everything. It's so many. Finally, climate change and urbanization, urban construction projects, road. This is why actually leishmaniasis is a public health puzzle. It's not just one challenge. It's a web of challenges that need actually what we call multi-sectoral solutions. But I want to point out into vector control, and that's where we're going right now. One of the main point for not gonna say sorry, control and surveillance is actually surveillance. It's monitoring on sunfly populations. So this is the medical entomology lab, and is a specific lab that is dedicated as a national public health function. We are in charge of the national surveillance of different type of vectors, not only sunflies, but also mosquitoes, ticks, and other insects, together with the Ministry of Environmental Protection and with the help also of the National Park Authority. We carry together a huge work that you will see more now from Alon and Shirley also, or what we do. And here we collect some flies across regions, we sort, we identify species, we map seasonality hotspot and build risk models. This data goes directly into the decisions about outbreak and response or preventions. Actually, this is where a lab like a medical entomology lab related to a government actually is critical. In a university, for example, you can do a brilliant actually PhD in 3-4 years, but an outbreak is not going to wait until we publish a paper actually, or publish our thesis. Here we need the real-time standardized national data, and that's why a government-led entomology public health provides. So what I forgot to put here, that also we have a National Center for Leishmaniasis reference that actually we are monitoring the whole human cases together with the epidemiology department. And our national surveillance starts with a huge data collection in the field. Together with the Ministry of Environmental Protection, they go to the field, and place the traps. We use we use a system that's called Mentor, that is actually an in-house developed based on a GIS application that is collecting data on time from the field. Wherever we place the trap, the data appears straightforward, it's just straightforward on the database. Then that trap comes to the lab, and you will see what happened. That is just to show you the amount of data we have to across Israel. That is not only some flies there. You can see some flies, mosquitoes, ticks, ants, a lot, mainly some flies again, I guess. As for the main surveillance, we use two different kind of traps that are available on the market, let's say, and we have lead CDC light traps and modified CDC trap with CO2. Our gold standard is CO2, and I would say why. But as you can see, every trap is barcoded, so we can actually read the barcode, record the trap location, and everything around the trap, and that goes straight to the web. As I say, we use a CDC trap with dry ice as a bite. These traps are homemade. They are operated at low voltage, made with dry ice, as I say, very close to the ground, down the draft position. That means that the sucking aspirator goes very close to the ground. They are more accurate in information about dissemination patterns of some flies in the field. They attract and collect a significant number of flies. They are simple to set up. They operate in the field. Just use a small two AA batteries. The traps are built with a stand. For some reason, that's something that deserves sort of research. Light traps are not working as is expected in these areas. So we found that dry ice or CO2-based traps are the most appropriate for our work. Some picture from the field work when the traps arrive in the labs. As you can see, they're very carefully treated. We can collect thousands of sunflies, as you can see on this spreadsheet. This is actually not a lot. They are counted, they are separated, they are allocated one by one. We use morphology for identification, but also we use molecular taxonomy for when we have to identify. We need to take into consideration, since this is a public health lab, we need to give an answer to every trapping session they have made. So we have a specific turnaround timelines that we need to stand for, and we have like around 30 days to give the results all the time. So if we get like in a week more than 10,000 flies from different places, we have only 30 days to process them and actually give the whole results, not only the number of flies, but also the species number and blood meal identification and Leishmaniasis infection rates. So here's where actually we are. It's becoming more interesting, all this talk, I guess. So far, we have focused on monitoring till now, and I explained the whole transmission dynamics in Israel. And in many ways, actually, monitoring is already the top control strategies that we can use to prevent specific outbreaks. Because without surveillance, actually, everything else is blind. Monitoring tell us which vectors are present, when they are active, which parasite they are carrying, where these reservoirs are. Actually, it's the foundation of any effective response. But surveillance alone doesn't actually stop the disease. Once we know the cycles, we fence the hard part. We can actually do about what we can actually do about it. And here is where it gets complicated. Control strategies are difficult to classify neatly. Okay, it's so hard. It's not like mosquitoes. Mosquitoes, somehow we know where mosquitoes breed. We can actually treat the immature stages. We treat the mature stages in a specific situation. But with some flies, as you saw from what I've said, is so complicated. Some of these strategies are established, some experimental, some they work, some that we don't know. And one of the most powerful drivers of transmission is not like actually the flight itself. It's actually us. We need to look at what we do to cause all these outbreaks or to generate actually those um, contact hotspot for transmission. Construction, development, urban expansion reshape the environment, and increasing its carrying capacity for reservoirs is actually one of the main points. For example, rocky hyraxes thrives on artificial habitat like retaining walls, quarry rock, pile created after constructions. Rodents find food on shelters in distributed soils and construction waste sometime. Those early bulldozers that reshape the lands also reshape the disease ecology. We can't just look at the flies. We need to look at the urban planning, construction, landscape design. Uh, uh, with this in mind, actually, we can go and walk through different control strategies. Um, so as you can see from this table, don't look at that. I was trying to put all the control means that exist not only here but around the world in one table. It's so hard. It's not possible sometimes. It needs more work. But for us, what is work is divided into life cycles. So that's what we're gonna see. We're gonna see reservoirs and vector control strategies for Leishmania major, for Leishmania infantum, and for Leishmania tropica. For Leishmania donovani, I cannot put into that because I just found it and we don't know what to do with that for now. But for Leishmania major, as I explained before, the main life cycles is actually involved rodents. And when the host, and here is a trick because we have protected hosts and not protected hosts. Those protected hosts with, for example, fats and rat, they're protected in Israel, so we cannot kill them. So we need to do some sort of activities in order to push them away from areas where they can call like a contact hotspot areas. So we use habitat management, which is reducing the reservoir and carrying capacity. I'm not going to go through everyone, just to show you a big picture of the different control strategies that we are using. Some of them they are experimental. Some of them they actually work. Alona and Shirley are going to give you some examples about them. That is actually the big picture. It's not enough to kill flies or treat patients or poison rodents. As you can see here, we need an integrated, it's actually a One Health approach, actually linking the environment, wildlife, human health, urban design. That's why isn't a just science, it's a public health in action. It's a build piece by piece like a little puzzle. As for Leishmania tropica, also we have habitat management, which is reducing the reservoir carrying capacity and the reservoir population management. And as you can see here, it's everything related to the host habitat areas. The vector control is mainly the same for every sunflies, although, for example, just to see IRS is not very well used, it's not used at all, and, or ORS, like outdoor residual spraying, some places they use, but like it's not working at all, especially in areas like in Israel, well, it's very hot and the UV is very high, that actually not good for the insecticides. As for Leishmania infantum, as you say, we have reservoir management and habitat management, as we saw before. Use of collars, tropical repellent, dog vaccination, which is wherever it's available, whether it's work or not. Systemic screening. So we have domestic and wild. Sometimes some authorities, they do wild kind monitoring to see the infections. As urban and rural areas actually are expanding, we don't just change the landscape, we change the disease ecology. Hyraxes in this point are confident to the wild. Before they were confident to the wild, now with expansion of the cities and rural environments, we can see them in our gardens. As you can see on these cute pictures, we just this is nearby Jerusalem. You just go on artificial rock piles, and you can see them on the backyard. So you don't need to go to you don't need to go to the wild to see them. You just see them everywhere. And for us in public health, that actually means our job. It's not just a surveillance. Just to remind, hyraxes are the main reservoir of Leishmania tropica, so we will see some samples or study cases about the how do you say, prevention or control of Leishmania tropica. I will leave you with Alon from the Ministry of Environmental Protection, which is going to be happy to present you and show you some study cases on this matter. Please, Alon.
Hi. Well, some of the things I wanted to talk about, Oscar already spoke about them, so I wouldn't say too much about it. But generally, Leishmania tropica, I work in the western part of the country, and this was the most recent place where Leishmania tropica was found. It was found before in the eastern slopes of the Samarian Mountains and the area of the Sea of Galilee, which is not my area. But when they arrived to the western parts of the Samarian Mountains, I started working on them. This was about more than 15 years ago, quite a long time ago. The reservoir, as Oscar said, is rock hyraxes, and the vector is, especially in our area, is Phlebotomus sargenti, and in the north of the country, it's also Phlebotomus arabicus. The places, the hyraxes are natural to the habitat, but naturally the population were very, very small. Since they don't know how to dig burrows, they live between rocks. They can live only in places where you have like cliffs or very rocky terrain. And most places in the Samarian and Judean mountains, you have the rocks. The natural habitat is that the rocks are inside the ground. So you don't have so many natural places where the hyraxes can evolve. And there were some mistakes in construction that because of those mistakes, the population of the hyraxes exceeded, and then we had the problem of the Leishmania tropica. Now, what are the possible solutions? Is sandfly treatment. Until now, it was partially successful, and we didn't pursue this direction. But maybe if we have time and money in the future, we might do so. The main solution was removing hyraxes and destroying the habitats, the artificial habitats of the hyraxes. We do not touch the natural habitats. If there is a place where hyraxes live naturally, we leave them as is, but we try only to change and fix the places where there were mistakes done with construction. And this is the main method. Next slide. Shirley, next slide. I don't have any control on the slides.
Sorry, just a second. It's Oscar on the slides.
Okay.
A second, I'm sorry. Just wait a second. Okay.
Okay, now the first thing we try to do is to treat those rock piles. The problem was, if I start before how those rock piles became to be, is mistakes in construction. What they do when they want to build a village, usually they come with a bulldozer and they push the ground and the soil because they want to have the ground flat. And what happens is that the big rocks start falling down the slopes. And the bigger the rock, the further it goes. And eventually what you have is outside of the village, you have like belts of boulders, which are excellent place for hyraxes to live. And from there, they also invade into the village because there's a lot of gardening and there is much water and the food is much tastier than in the arid areas outside of the villages. Now, what are the ways that we tackle this problem? One of the things is crushing the boulders and removing them away. Some of the boulders, if you crush them, you can use the rocks later on, or the gravel that you get, depends how you crush it, and you can use it for construction in another place. Another way that you can see in the picture is crushing and compacting. If you don't want to take it away, you can use a pneumatic press, and then press the crushed boulders into the ground, and this way you don't have places where the hyraxes can live. Another way is removing the boulders. Sometimes boulders can be used in other places, for instance, in construction of breakwaters, in ports, or other places that it can be used, places where Leishmania tropica is not likely to be found because there are no hyraxes, places where are not rocky places. Another way is burying the boulders under piles of dirt. Sometimes they have a lot of dirt that is left after construction, and then you just put it on top of the boulders. It doesn't always work because sometimes you have like gaps that contain air, and when in the rainy season, the air can go make the ground penetrate the rocks, and then you might have you need to fix it and make some changes. Another way is covering with nets. This was completely unsuccessful. The hyraxes are very good in finding little holes that they can go under the nets, and then you see all the hyraxes under the nets, and this way, not only that they have shelter, they're also protected from birds of prey and other enemies that they might have. Another way that can be done is spacing boulders, especially when you don't have many boulders and you have them piled. If you space them, then you don't have crevices between the boulders, and then there is no place for the hyraxes to live. Next. Another problem is retaining walls. The best way to build retaining walls is in a way that you don't have holes that can be habitat for hyraxes. But sometimes, in many places, they use boulders and pile them one on top of the other. This way, you have holes between the rocks, and the hyraxes go inside and live there, and from there, they can go into the village. So the best way, if the retaining wall was not constructed, to build it in a way that you don't have voids. Another way, after you have the walls, is filling the holes with concrete, which works quite well. Covering with mesh was not very successful, and also it's very ugly. So this is not a very good way to do. Another way is to put soil into the voids and planting suitable plants that have like a strong roots. And this way, this looks most natural. This way you can have like walls that don't have crevices for the hyraxes and look more natural than filling it with concrete. Next. Here you can see how it looks covering with mesh. It's very difficult with big boulders. And sometimes here you can see in the picture on the right, you can see a little hole. It's not covering completely, and from there the hyraxes can go in. And you have some birds of prey that can eat hyraxes when they sit on the rocks. And this way, when they are under the net, not only that they have a good habitat, they're also protected from birds of prey and foxes, jackals that can also eat, especially the young ones. Next. Here you can see this is from the north of the country, from the area of the Sea of Galilee. the way that they take the rocks and mostly crush those rocks and take them to another place. In the north, most of the rocks were basalt, volcanic rocks, and they have a lot of demand in the market. So financing taking the rocks away was quite easy because the constructor that took the rocks got permission to sell the rocks. So he also did some profit out of it. So those projects were very good. We didn't need to finance them. Next. Here's another example of construction. It's quite intensive and it takes quite a lot of time until it's done. Next. Now, in 2011, we made a little booklet of a guidelines document for reducing exposure to rock hierarchs. This booklet was especially made for people that work in construction, how to build in a way that you don't make habitats for rock hierarchs. Here there's a QR code. The document itself is in Hebrew, but there are lots of ways that you can, if you're interested, you can translate it, like ChatGPT and so on. If you have any questions about it, feel free to ask in the future, no problem. I'll try and answer. And the next thing is an experiment we did with electric fence, which was extremely successful. The idea was that we want to stop the hierarchs from getting inside the villages and letting them get out of the villages. So what we did is usually most of the villages have fences around them, but the fences do not stop hierarchs. They can climb the fence very easily. And also many times there is like a narrow passage beneath the fence. So for the hierarchs, it's no problem to pass those fences. We did some modification. One is to put a concrete belt at the bottom of the fence. The other thing is to put an electric line like you use in places where you grow herds of sheep and cattle and so on. And only one line at a height of about 1.5 meters above ground. And this line would be on the outer side of the fence. Now, what happens is that the hierarchs, when they want to go out, they climb the fence and then they jump to the other side. Or even if they go down, here you can see this is not a fence of a village, it's a fence of a home, but the idea is the same idea. Can you go back, please? So what happens is that like the hierarchs that goes from the inside and wants to go outside of the village to go and eat or meet his friends that are outside, the electric fence doesn't stop him. He either jumps, or if he goes down the fence, the moment he feels the electricity, will just fall out. And the hierarchs that wants to climb in climbs until the point where there is the electric line. He gets a small zap and he just falls out and he doesn't go there anymore. The idea is to have it at least 1.5 meters above, that the hierarchs cannot jump above it, and that it will be at least 30 centimeters less than the top of the fence. And the idea is that if you have the electric line at the top of the fence, it would prevent the hierarchs from going outside, because once they climb the fence, they will hit the line and then go back again. So it's very important to have the electric line on the outside. And this way you have the hierarchs going outside. Now, in a village or in any habitated area, you have entrances. And the problem is you can't put a fence on the entrance. So how do you avoid getting the hierarchs coming from the entrance of the village? So what we did is we did some kind of corridor of at least 50 meters of fence that is just close to the road. And you have electric line going all the way. So hyraxes that are going along the fence from the outer side are afraid to go these 50 meters because they see it's a very narrow area and it frightens them. So this way, they do not go inside. And if you take care of this fence and the fence works, it's an excellent solution. Very, very, very easy and quite cheap to maintain, much easier than the rock piles. Next. Now, here are the specifications of the fence. You can see on the left picture. It's a little bit hard to see. You see this line just beneath the middle of the post not the post, the middle of the picture. Yeah, this. Yeah, can you show it? It's quite hard to see. Anyway, this is the line. Yeah, this is. You can see also the insulation where it passes. Okay, and there's few things to see, and you can see the cement on the bottom of the fence. This way, if it's treated well, the hyraxes cannot go in, and they easily can go out. So we don't need more than a single line, and the line is located outside. Usually, it's preferred to have like 5,000 volts or 10,000 volts. And this way, even one source of electricity is enough to cover a small to medium-sized village. It's very important to take care of the line that this is one of the problems that we have. It's kind of like the behavior of the population. The people that take care of the fence sometimes are not doing their job well. Sometimes there is construction work, so the lines get cut. So it's very, very important if you do such a thing is to take care of it, like proper maintenance every week, to come and inspect the line, to see that it's working properly. And after rain, when it's more problem, then you might have sometimes the water can go beneath the cement belt. So it's very important after rain to check that there is no problems and that the hyraxes cannot go in. Okay, next. Here's another example. Okay. I can say one thing about, okay, and another one, go to the next slide. I tried to make places that the hyraxes can go outside. If you look at the picture at the bottom center, there is like a pipe, and in the end of the pipe, there is like a door that has an axis on the top of yes, this one. So on the right side, you can see it's like cut 45 degrees. No, not this one. This is the camera that photographs it. You see that the right side of this red pipe has it's closed from the right side, yes. And it has an axis from the top. So if the hyrax goes inside, it just pushes the door, goes outside, and then it closes and he cannot go back. So the idea was nice, but we didn't see any hyraxes going inside, and we had some problems, especially with kids throwing sticks and stones inside those pipes. So we neglected this option. Also, we saw that the construction of the fence is very effective to make the hyraxes go out. Even in one village, we had all the hyraxes going out of the village without doing anything active to take them out. Here you can see also gates, and they also have to have the electricity and water passages on the bottom left. It's very, very important that the cement will not block water passages, because water is very, very strong, and if you don't have good water passages, then you'll have land erosion, and there will be new holes for the hyraxes to go back. Okay, next. I'll speak about, I'll give one example of, this was the first village. It's in the western slopes of the Sumerian Mountains, which we had Leishmania tropica. The amount of Leishmania tropica, the amount of sick people were the highest in Israel at that time. It was a very small village and many people got Leishmania tropica. What we did there at the beginning, we tried to take rock piles out, but it was very difficult. There were too many rock piles, and because the location of the village was a very rocky place. And then we did, this was the first time we tried to put an electric fence. It was very successful. It was the hyraxes, some of them left by themselves, just climbed the fence and got out. Some were captured and some were hunted. And eventually you had hardly any hyraxes inside, but there were quite a lot of hyraxes out of the fence. And you can see the results, the amount of, you can see that by 2015, we did quite a few captures of sandflies, and none of them had Leishmania tropica. And this was amazing. Like, we got from a very high risk, we got to zero. And this is a case that was very successful. And later on, in many other villages, it was also very successful. And using electric fence is simple. It's not dangerous because the electricity is very high voltage, but it comes in pulses and in very low voltage. So it hurts, but it hurts only for a few seconds, and it only deters the hyraxes, but it doesn't harm them. And also, if people touch the electric fence, nothing happens to them, beside a very sharp, painful zap for a very short period of time, like seconds. After seconds, you don't feel it anymore. So this was the first one, and this was very successful. And later on, it was done also in many other villages, and some of them, all the hyraxes, there was no need to capture them or hunt them, because the hyraxes got out by themselves, and then we didn't need to do anything else. Next. Another case is in another village where we tried to do a barrier. One of the problems of this village is that, like, outside of the village, there was a place with a gigantic place with many boulders that there was no chance that we'll have the budget to take those boulders away. And what we try to do is make a fence that on top of the fence there is a net, and we try to spray the net with a mixture of insecticide, bifenthrin, and sugar to attract the sandflies to eat the infected, to eat the sugar with the pesticide. You can go to the next one. Here you can see how it looks. If you look at the map, you can see that, like, you see the area in blue and red. This is the area where we put the net, and on the right side, those were very big rock piles that you can't see here, but there were too much to take away, and this is the spraying of the mixture of bifenthrin and sugar on this net. Next. We did it for some time, and now you can see on the right the rock piles, but things change. You can see, I won't go through all the numbers, but you can see that in 2015, the risk was much less considerably, and there were much less females of sandflies going outside, like from the rocks into the village. But what happened is they started to build a new neighborhood on where the rock piles were. And you see those gigantic trucks, they started passing near our nets, and they got covered with dust, a stick of maybe 5 millimeter, 10 millimeter of dust, and the experiment was gone. So we think it is a possibility in places where you cannot do other things. It's an option that might be successful, but from what we did over there, it was not enough. It was not enough. We did some other experiments that I didn't bring it here because they were not successful, but they have some kind of, maybe they will have some future if you try to make some modifications in the future. We try to disperse CO2 along pipes for along the fences, and to try and exterminate the flies that are attracted to the CO2. We solved the problem how to disperse the CO2 for a long distance, because one of the problems is that if you use normal dispensing methods, you'll have most of the CO2 going outside in the first holes, and then it gradually decreases. So we solved this problem, but we didn't have we couldn't decrease the population of the sandflies sufficiently that it will be effective to make a change. So that's about it. Okay, thanks.
Thank you, Alon. Thanks a lot. Very interesting. It's a lot of work, they say, and as I said at the beginning, is a completely engineering activities we have to do here to control Leishmaniasis sometimes. I will let you now with Shirley, that she's going to talk about a specific case study, very interesting also. So Shirley, please.
Okay, we'll keep it short, but can you move to the next slide? Okay. I will try to be very, we don't have enough time, I think. No, we have very short time. So I'm going to talk about a study that we conducted in 2013 in the semi-arid area of the Negev. And we'll talk about the distribution and dispersal of Phlebotomus papetazi and rodent reduction activities in zoonotic cutaneous leishmaniasis foci in a semi-arid area. Oscar, can you move to the next slide, please? Okay. So this is the area. We are talking about a very small cooperative community, kibbutz, with only 500 residents, and it's located where you can see in the Negev. And if you look at the next picture, just in the middle, you can see that this is some sort of an island of nice residential homes with cultivated gardens and lawns. And just around it, you can see just a sea of agriculture fields. Important point, this is the main suspect you can see on the right side of the slide. This is an embankment that was just around the kibbutz. It was just that cars won't move or try to get into the kibbutz. A dust road and a fence all around the kibbutz. And now you will see. Oscar, can you move to the next slide, please? So it used to be a regular kibbutz until and no disease at all until 2009. But in 2010, there were 47 cases of Leishmania major in the kibbutz. And you can see that the incidence rates were 103 to 10,000 residents, which is very high incident rate. Just happening all of a sudden. It was an outbreak. And you can see, I will just remind you, on the right, you can see the transmission cycle of Leishmania major. We had we have geards. In this case, we have geards. We also have other rodents considered to be a reservoir for Leishmania major. But the geard or Marionus tristrami is a pest, is a rodent pest, and it's usually eating in agriculture fields, and it is considered to make damage. And the vector is Phlebotomus puppetus. Oscar, can you move to the next slide? Okay, so as I was saying, we were having an outbreak in 2010, and in 2011 we had a large survey in the area and serving sandflies and the geards. And the results, or the assumption was, the observation was that many active burrows are on this embankment just around the kibbutz that's surrounding the residential area. As you know, all know, the assumption is that sandflies, they don't progress, they don't disperse in long distances. So that's why it was assumed that it should come from this embankment. The sandflies, or the infected females, sandflies should come from this embankment. Okay, so they decided, what was decided to do was just to create a cordon sanitaire, which means to create a buffer without any infected geards around the kibbutz, and this will solve the problem. But the thing was that in 2012, we got this money for research for a 3-year study. So we decided that we should check if this is actually the source, or if there are other locations that can be the source for the infected females and contain also infected rodents. Oscar, can you move to the next slide, please? Okay, so we had a few questions in this study. The first question was, what is actually the land use that is most preferred on the sandflies, where we can find most of the sandflies that are coming from? So we are replacing for 14 nights in a row during the summertime, during the high season. We're replacing 55 traps in different locations. As we mentioned, Oscar mentioned before, we placed CDC traps with CO2, weighted with CO2. And Oscar, can you now please? So on the right side of the slide, you can see the map. Okay, Oscar, can you just move to the next? Okay. So the yellow dots are the residential area. Okay, and you can see there are a lot of lawns and nice small houses. So we were putting traps over there. Then we were putting traps on the embankment area, and as we were saying, this was the suspected area to be the source, or the main source. And after we were putting traps in the agricultural area. Oscar, can you move to the next? Okay, so this is the agricultural area. You can see that during summertime, it's not not a lot of growth during summer, but mostly plowed fields. And the last area was the green dots that are in the natural area. So it was, that was the first question. Can you move to the next slide, please? Okay. The second one, question that we had was whether the sandflies can come from outside the kibbutz, or there is any other source. So we wanted to know how far they can fly. Are they affected by the wind? If there is certain direction they are coming from to the kibbutz from. So in order to do it, we use this nice method, which is her main advantage is that you're not doing, you don't have to do capture and recapture and release after, and so you don't have to intervene their natural behavior. So what we were doing, we chose 5 points where we have high yield of sandflies. from before. We were doing this experiment during October 2013. Okay, so we were just spraying an area of 200 square meters, sorry, with 20 liters of solution with 5 different colors. Okay, at the first night, we were putting inside this area, we just mentioned that we sprayed mostly vegetation. Here you can see a lawn, which is just on the right side. We were spraying vegetation and dead standing vegetation mostly. And at the first night, we were just putting CO2 container with CO2 and didn't put any traps at all. In the 2 following nights, we were putting traps in 18 locations around each point, which I will just show you in a second. And we were, and now you can see the, I will show you the results. Oscar? Okay. Okay. I will just mention what that of course all the sandflies were sorted and defined in our lab and were identified for Leishmania in the lab. So those are the first results. I will show you now the habitat preparation. So on the right you can see the map. The triangles represent the minimal infection rate. And the circle represents the maximum sandflies. Can you go back, please, Oscar? Just okay. The maximum number of sandflies per location. Okay, so as you can see in the residential area, you can just move on now, Oscar. Okay. Okay, in the residential area, the number of traps and the mean number of sandflies was really high, really low. Hardly any sandflies, and the minimal infection rate was very low. So it means that it's probably not a source. Okay, on the boundary area, the embankment, you can see that we had sandflies from there, and there was infected females over there, as you can see from the minimal infection rate. But what was much more significant was the agricultural area, where the numbers were much higher of sandflies, the densities were higher, minimal infection is higher. And if we would like to explain it, the reason is probably that when we have these plowed fields during summertime, we have a lot more resting place and development place with the ultimate conditions of high moisture and organic matter available. And over there, sandflies can develop, so the densities were much higher. And the last area was the natural area, Eshkol National Park. You can see that you can move to the next. Okay, the minimal infection rate is much higher, and we believe that the reason the minimal infection rate is higher in this area is because probably rodents and sandflies develop in the same location. The only available location for them to develop is in the burrows of the rodents. Oscar? Okay. So the results of the sandfly dispersal. So I will now explain what we see on the left in the maps. So the one location that is marked with a star, that was the area where we marked with color, okay, where we sprayed with color. And the other locations were locations where we trapped marked sandflies in the same color, okay? In order to know what is the distance and to calculate the mean distance traveled of the sandflies, we were putting annuals, some kind of ring around the area up to 1 kilometer from the center of the area, which is the area that we marked. So as you can see, in most of the cases, in most of the colors, except for the blue one, the sandflies disperse to the farthest trap and arrive to the first trap. And the maximal distance that females arrived to were 1.81 kilometers and 1.53 for males, which is probably a long distance for creatures that consider to be only just hopping and gliding around. And the minimal, the mean distance traveled that we calculate was 0.75, which means this is actually the significant number, because it means that most of the population, or at least most of the population, can cross this distance, and it means that the sandflies can actually come from the field. What we also can see here, that sandflies can fly to all directions, and wind in this area, which is usually from western north to eastern south, didn't affect, and they were coming from all directions. Okay, Oscar, can you move to the next slide? So just to conclude, I was saying most of the things, but what we saw that our primary hypothesis was not correct. And the embankment is probably not the only source and not the main source of the sandflies. So what we needed to do right now is just to expand the cordon sanitaire to the agricultural areas. Okay, to the agricultural field. And Oscar, move to the next slide, please. So we decided to take care of our bets, just to do some sort of control actions in the fields against rodents in order to know where to do this. There were surveillance of rodents with trapping and surveillance of burrows, and the conclusion was that most of the burrows, or the concentrations of burrows, were around this pink trail. So move to the next one, please. So we were applying rodenticide in this next to the burrows aggregations. And in addition, we wanted to avoid another places for development of rodents, so we remove soil piles near the kibbutz. We were doing, the people of the agriculture were doing soil cultivation right after harvest in order to avoid burrows in the field. And additional nice thing, which is considered to be very ecological, and it's used a lot in Israel, is using barn owls. In Israel, we just place barn owl nests in the field, and you can know that those barn owls can eat up to 10,000 rodents every season. So it can be effective, but it can be just used alone. So it's some sort of IPM. Oscar, move to the next slide, please. And we also were taking care of the embankment, doing just similar measures, just to remove the burrows and the vegetation from this embankment, if it's also a source. Okay, so I will not just read the summary, but I will say that it costs a lot of money to do all these activities, and it was done for 1 year. But of course, in order for it to work, you have to do it over and over again. But there is some sort of it can be efficient. That's it. Thank you very much.
Thank you, Shirley. Thank you, Alon. That's very interesting. As you can see, it's not only these kind of samples that Alon and Shirley talked about. We have so many others, like external wall shelves to stop the entrance of flies, or some flies inside a human environment, fences around houses, so many other different approaches. Shirley pointed out they're very expensive. you don't do that only once and you just find a solution. You have to then do it over and over. And also, actually, what Alon also pointed out, those actually means you have to maintain them, and the maintenance sometimes is a commitment of the society, of the community through that mean. And sometimes it's where human behavior plays a huge role in all this game. So here is the big point: Leishmania major adapted to voles as the new reservoirs. Some flies activities increase in untreated fields. Human cutaneous leishmaniasis cases emerging farming villages nearby. Actually, this is a striking example of how actually human choices reshape parasite ecology. And it's not controlling leishmaniasis, as you saw, it's not just killing hosts. The elements are very tight connected to each other. And this is the essence of the One Health. Farming affects rodent, rodent affects sunflies affects humans. Every action in agriculture or urbanization planning is actually cascaded into public health actions or into public health structure. And in our communities, what we do here together with the Ministry of Environmental Protection, Park Authority, Ministry of Health, we map these cascades. One Health is not just a concept; it's our reality. So it's very important to take that in consideration and this concept as a whole. And I wanted to say thank you to the Israel Natural Park authorities, which are all the rangers that they work with us. I didn't write the name of everyone, but they're like this is the heart of the field control and surveillance. Thanks a lot to the Ministry of the Pest Control Division, Israel Ministry of Environmental Protection, Dr. Shai Reicher. He's the head of the division. Tamar Yeager, Dani Shalom, Alon Ber, who is here, Hamsi Habiba Allah, Anna Bebina, Dobev Hangari, and thanks to the medical entomology and parasitology lab, that without them, actually, most of the sunfly classification and what we do here for the lab surveillance is not going to happen. Thanks a lot to everyone. This is actually my team. And thanks to the whole Klimas community as well. Any question?